let's take a look at charge, Coulomb's law, and the electric field. So charge, what is it? Well, it's a little bit difficult to define. It's kind of hard to pin down. It's a little bit like trying to define mass. What we can say about it, though, is that it's a property that some objects have. No, that's not very satisfactory, but it's true. It can be positive or negative, and we know that opposite charges attract each other. So it's a little bit like what we saw with gravitational forces between masses. However, we also know that with charge, like charges repel each other, which is quite different than with gravitational forces. Gravitational forces could never be repulsive, but like charges repel each other. We know that charge is conserved, which means that it cannot be created out of nothing and it cannot be destroyed into nothing. And the total charge in a closed system is constant because charge is conserved. All right. The unit of charge is the Coulomb. It's usually written as a C, capital C. However, a Coulomb is a very large amount of charge. So usually when we talk about charges, we're talking about millicoulombs or microcoulombs or even nanocoulombs. Common symbol used for charge is a Q. Don't really know why, but it is. So sometimes charge is represented with a capital Q or a lowercase q. Another strange property of charge is that it is quantized. That means it comes in multiples of this quantity called the fundamental charge. So we can have, 2 times the fundamental charge, or we can have 5 times the fundamental charge, or we can have 1,516 of the fundamental charge on an object, but we cannot ever have half of the fundamental charge on an object, or 5.2 of the fundamental charge on an object, or 1/100th of the fundamental charge of an object. It is quantized, meaning it comes in these lumps of the fundamental charge. All right. So Coulomb's law. Coulomb's law is the way that we determine the amount of force that's on a charge due to another charge. And I'll write it down here. F is equal to K Q1 Q2 over R squared. So F here is called the Coulomb force or electric force or electrostatic force. But whatever you call it, it's that force that's acting on, say, charge Q1. K is called the Coulomb constant. K is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Q1 is the charge that's feeling that Coulomb force or electric force. Q2 is the charge that's causing the force on Q1, and R is the distance between the centers of the objects. So if you look at it, it looks pretty darn close to Newton's universal law of gravitation. It's got that 1 over R squared going on. It's an inverse square law, just like Newton's universal law of gravitation. And also, like Newton's universal law of gravitation, it assumes that the charges are points, which is a very good assumption when the distance between the objects is much greater than the size of the objects. Or, like in Newton's universal law of gravitation, when we have spherically symmetric distributions of charge. Now back to this weird constant K. If you notice, K is a pretty big number. But K is kind of used by students. It's not used professionally. For reasons we're not going to get into, the Coulomb's law is often written, instead of with K, with what K is equal to. K is equal to 1 over 4 pi epsilon naught, where epsilon naught is another constant called the permittivity of free space. And the permittivity of free space is 8.85 times 10 to the minus 12 Coulomb squared per Newton per square meter. Now, we're not going to get into why 1 over 4 pi epsilon naught is kind of the preferred thing in the professional world, but just know that it is. Okay, so in Coulomb's law, if we get a negative value for the force out of this thing, then that implies that the force is attraction, that it's an attractive force. And if you look at the equation, you can kind of think about why, because if we have opposite charges, if one charge is positive and one charge is negative, then we're going to get a negative value for F, which means that the force has to be attractive. If you get a positive value for the force here, then that implies repulsion, because that means that Q1 and Q2 have the same sign, and they have to repel each other. So let's take a look at an example. Let's say we have two charges, Q1, Q2. Here's 1 microcoulomb, and here's -3 microcoulombs, and they're separated, or their centers are separated by 2 centimeters. So let's see. Let's find the force on the negative charge. The force on the negative charge. Well, F equals K Q1 Q2 over R squared. Put in K, put in the 2 Q's, put in the distance between them in meters, convert to meters, and then square it. And we would find that this force is equal to -67.4 newtons. Remember, the negative tells us that it's an attractive force, which it should be. We have a positive and a negative charge, so they should attract each other. But that's what that negative sign is telling us. And there we go. So 67.4 newtons toward the positive charge. And if we were to find the force on the positive charge, by the negative charge, by Newton's third law, we should get the exact same number, just in the opposite direction. So the force on the positive charge is 67.4 newtons toward the negative charge. All right, well, that's if we have 2 charges. What happens if we have 3 charges? Well, same thing as if we had 3 masses. So if I have a negative charge, a positive charge, and a negative charge, and I want to figure out the force on this positive charge here in the middle, what I would do is I would find I would find the force on that charge by the first one. Okay, force on 2 by 1, and then I'd find the force on the second one by the third one, force 2, 3, and then I'd add those 2 forces together as vectors. Okay. Now, the electric field. The electric field is defined similarly to the gravitational field. The electric field is equal to the electric force, or Coulomb force, per charge at a location. So the unit then for the electric field, if we look at the units here, force has units of newtons, Q has units of coulombs, so the electric field has units of newtons per coulomb. All right, so that's the electric field. If we have a point charge, the electric field that's created by a point charge, well, we have an equation for the force caused by a point charge. It's KQ1 Q2 over R squared. And if we put that into the electric field equation, we can get an expression for the electric field caused by a point charge. It's KQ over R squared. Now, another thing that we can say about the electric field is that it always points away from a positive charge, and it points toward a negative charge. But then what do you do if you don't know where charges are, and you're trying to find the electric field in a region where, you don't know if there's positive charges here or negative charges there? Well, then, what we say is that the electric field points in the direction that a positive charge would feel a force. So if you imagine placing a positive charge at a location, the direction that a positive charge would feel a force at that location is the direction of the electric field. And kind of a corollary to that is that if we placed a negative charge at that location, the electric field would be in a direction opposite of the direction that the negative charge would feel a force. Now that might seem a little bit cumbersome, a little bit awkward, but we're going to get a lot of mileage out of that idea.